Hello, my name is Mindel Nirveli Rodriguez Granados, and I'm going to present the problem situation. What we have is a straight tank reactor, and the reaction that is happening there is a second order exothermic reaction, which basically means that the reaction is releasing energy in the form of heat. And as we have a heat release, it has to be controlled through a cooling jacket. Otherwise, the heat could build up and cause the tank to explode, which is quite dangerous. So what we are looking for here is to regulate the temperature in the tank, and we want to maintain it constant, and this could be reached thanks to the jacket. Also, we want to control the concentration of the reactant A in the outflow. And we need to know that all reactions have different conditions to be carried out. So if the temperature changes, our reaction may not have the same concentration, or the reactant can be all consumed. Sometimes operating reactors with an exothermic reaction can be extremely risky for people, so the need for an automatic control could make the process safer, and also will note when something is not normal. So here we have the representation of the tank, and what we have is that the flow that is entering, it's going to be the same as the flow that is out of the tank. So the volume is going to maintain constant. Also, we have other different variables as the concentration, temperature, and flows, other flows. But in this case, we only can control the flow through the tank and through the cooling jacket. In this simulation, we have the same tank system as the last slide, and we can see that we have all our inputs and outputs. First, we are going to check if the system is in equilibrium. Well, here are the instructions. And for this, we have the next given values for each variable at the entrance. And also these equations that are here basically represents the derivative of the concentration of A, the temperature, and the cooling water state variable. So to see if the system is in equilibrium, the derivatives needs to be 0. To check this, we substitute the given values into the equations and making some calculations. And we got these values that are here. And in the case of XA and XT, and we almost got 0, but in the case of C, we got 0. And being these values almost 0 and 0, we can say that the derivative is 0, which means that the system is in equilibrium. To prove this, we run the simulation and got these graphs for XA, that is on here, and for XT, that is this yellow line, and XC, that is this blue line. And we can see that the behavior is constant. So we can say that our system is in equilibrium. Then to do this second part, we increase the input flow of the cooling jacket and the input flow of the tank 20% more at different times. And what we want here is to know which case is going to give us a first order behavior or first order response in our output variables. First, we increased the UF, that is the input flow through our tank. And we obtain these graphs for XA, XT, and XC. And we can see that they have a good first order behavior. On this next simulation, we turn the cooling jacket 20% more entrance, and we got these next graphs for XA, XG, and XC. Making a comparison between the two cases, which are quite similar, we can say that if we increase UC 20% more, the output variables are going to behave more like a first order response, because they are going to act faster, as we can see here. And they are not going to present a little decrease that is shown here. So to fit a PID controller, we got the first order response of the system, and we obtained the value of the delay for the time constant and for K. The values were obtained reading 1.165, that is this purple line, and 1.39, that is this line of here. And obtaining that values, we subtract them and we obtain GF. Then we use GF, the GF value, and that is 0.026, and multiply it by the 63% and by the 28%, obtaining T1 and T2. Then making a system of equations, we obtain theta and tau. Those values were used to find Kc, Ti, and Td of the Ziegler-Nichols table. And that's how we obtain P, I, and D. That are the values reported on here. So we add a PID controller and simulation, and we place the values of P, I, and D on here on the simulation and run it to obtain these graphs, which represents that our output variables reach equilibrium and our system does not represent oscillations, and that our error is pretty small. Then we have to value some criteria. We need to change the step in the effluent first. And well, here our step time was going to be 20, and our initial value was going to be 1, and our final value will be 1.5. So we obtain this next response for the output variables, and they look that the system behaves well and reaches equilibrium, as we can see here. Then on these graphs, that are on here, we change this step on the effluent concentration, which our system time, our step time, also was going to be 20, and our initial value will be 0.4, and our final value will be 0.2. And also we can see that XA responds faster and then maintains constant for a certain time and then goes down and maintains in equilibrium, which could mean probably the concentration obtained, it's not going to be the desired one, but we can see the temperature and XC reach equilibrium and maintain constant. Finally, we got these values changing the temperature in the effluent, and our initial value will be 1 and our final value will be 1.3. And we can see we have a weird behavior on XA, but then it established. Probably we can see the desired concentration is not reached until after some time. And then we can see the temperature and XC behaves as they are in equilibrium, just as we want. So we can see that modifying all these steps, the performance criteria is satisfied, since XA and XT are maintained constant and are in equilibrium. So the most valuable thing I learned in this course was how I can implement first and second order systems to be able to automate any chemical process, such as the one we saw in this problem situation. And since the field of chemistry can become dangerous, automation of processes is required to make them safer for everyone. Also, learning about control systems such as PID helped me learn that the system can be regulated and obtain the desired conditions of any process. Thank you.